So I'd like to just say that for those of you that don't know, I'm Keith Liddy, the president of the RINA London branch. And I'd like to welcome you all here this evening for this webinar presentation, which is actually the first presentation of our new season. Today's presentation is going to be sandwich plate systems, a structural composite, and it's going to be given by Ian Nash, the business manager of SPS Technology Limited. A little bit about Ian. Ian is the marine and offshore business manager for SPS Technology and works with a wide range of global clients advising on class-approved composite structural steel repairs. With the SPS Technology team, Ian is on a quest to ensure composite structural repairs are seen as standard repair options and no longer a new technology. Ian has worked on projects globally with most of the oil majors and taken part in a number of maritime research and development projects. After studying engineering at A-level, Ian joined the Royal Navy, and Ian qualified as a lead marine engineer on destroyers and studied marine engineering at Portsmouth University before beginning his 13-year tenure with SPS Technology. So we welcome you to RINA, Ian, and we look forward to your presentation. So if we can hand over to you and share your screen, that would be great. Thanks.
Thank you very much. Maritime industry's approach to vessel crack repair using composites. Structural maintenance on vessels is growing both in terms of demand and complexity. This requires a new innovative approach and an overhaul of decades-old approaches to vessel crack repair to unlock cost, time, environmental, and safety benefits. Repairing the cracks present on a vessel's critical structural components forms a key part of structural maintenance, which preserves asset integrity, ensures seafarer safety, and safe passage of cargo. The global shipping fleet is aging. New stress points are emerging on existing vessel structures as a result of retrofitting and refits. Work that is vital in prolonging the life of the vessel and ensuring cost-effective compliance with environmental regulations. These factors mean the demand for structural maintenance, including crack repairs, is greater and more complex than ever before. For many years, gouging and rewelding or crop and renewal techniques have been used to address cracks on vessels. While effective, the process involves extensive steel renewal, which is costly, time-consuming, and comes with a heightened risk and time out of service. With the average age of the world merchant fleet continuing to grow, as of last year, on average, it was 21 years old per vessel, there is likely to be an increased scope for structural repairs to address vessel cracks, with associated costs and time out of service, both key concerns. Time out of service relevant to cracks in this presentation talk about hull or fuel tanks specifically. In this presentation, we'll examine how the combination of these factors suggests an overhaul is required in the maritime industry's approach to vessel crack repair. While repair techniques have remained static for many years, structural composites offer a cost-competitive alternative that's fast, non-destructive, and delivers improved strength compared to conventional steel structures. There's three types that I've identified here on the slide. One is a temporary composite wrap repair. Damaged ships and offshore pipe structures can be repaired and protected against the effects of erosion, corrosion, and deterioration, while the wide range of polymer composites, using a wide range of polymer composites, polymer technology has been used in temporary composite wrap repair and maintenance of metal products since the 60s. Temporary composite patch repairs features an application of carbon and glass fiber mixed with epoxy resin or adhesive to damaged surface. By curing, the resin hardens and permanently bonds to the surface, impregnating also the fibers that reinstate the strength of the damaged part. This creates a solid new layer of material that provides full water tightness. These repairs have been around again, probably about 35 years. And then we've got the sandwich plate system, which is a fully class-approved permanent repair, strengthening and upgrading solution that has been used on marine structures for over 20 years. With SPS, two metal plates are bonded by a polyurethane core. Now, the picture that I've shown on this slide, none of those three repairs will solve that issue. The crack related to an accident or a collision where it forms a dent or deformation in the ship's structure. There's a geometric misalignment of the support structure and a crack forms at the weakest link. Obviously, this is the worst case scenario. Steel ship structures can develop cracks as a result of their all-welded construction or material imperfections, loading conditions, fatigue, and corrosion as they operate in highly corrosive environments. Welded ship structures are susceptible to damage during its construction and operational life. Design inadequacies, material selection, material imperfections, improper welding, incorrect fabrication, or poor workmanship are some of the probable causes for damages during construction, while fatigue and corrosion are related to operations. These damages primarily manifest as cracks in the ship structure, either immediately after fabrication or launching, or in due course of time. Crack formation or initiation appears inevitable or unavoidable, given the uncontrolled variables involved in constructing a welded ship structure, along with other factors, including the use of high tensile steel strength. So, where do cracks come from? Cracks can develop during the ship's construction stage. Due to their size, for instance, hairline cracks may not be picked up during the construction and addressed. Under normal circumstances, these cracks may not affect the ship structure integrity, but when unforeseen event takes place, like a collision with another ship, or a grounding event or impact from docking during bad weather conditions, these existing cracks could propagate at a faster rate and lead to structural failure and compromise the integrity of the structure, whether it be the ship's hull or one of the ship's tanks. When a crack is found in a ship structure during a routine inspection, or in some case by chance from a keen-eyed marine engineer on their rounds, the first thought is, what caused the crack? Is this the only one in the area? Is the day-to-day operation of the ship contributing to the cause of the crack? And what do we do to address the crack? We need to stop it growing, and we need to identify a suitable repair method so the same crack doesn't reappear after the repair has been completed. Accidents at sea in the past few decades have had a huge impact to the pollution and damage of marine life, in addition to the potential loss of life or potential loss of a ship at sea. Ships are designed and built to such stringent standards of safety and pollution prevention and extensive inspections during construction and while they're in service. So there's lots of safety measures in place already. Despite these safety measures, accidents continue to happen, sometimes with catastrophic consequences. Almost 40 to 60% of the accidents involving cargo ships are due to collision or grounding accidents. Human errors in operating and manning these ships is one of the primary reasons for the accidents. This exceeds other causes such as technical or mechanical failures, design issues, and environmental conditions. The shipping industry has to be cautious towards accidents, as there's no such insignificant leak which is acceptable anymore. In an extreme event, such as a collision or a grounding accident as a result of human errors or not, a high level of redundancy will be crucial in limiting the extent of the damages to the ship's hull and the potential for further unexpected consequences. If you look at a ship's life for cracks, you say the first 5 years as a ship comes out of construction, midlife will be 6 to maybe 10 years, 11 years, and then later on in life, we'll look at the last 10 years of a 20-year design life ship. Cracks reduce the local strength of the structure and compromise the tank leak integrity and structural integrity of the hull by increasing the global stress. These deficiencies may eventually lead to a rupture or fracture of the structural member over a period of time if neglected. Nevertheless, not all these cracks are serious, primarily because ships are very redundant and a tolerance is a function of the overall structural redundancy, ductility, and fracture toughness of the structural components. Cracks are not easily detectable. They can go unnoticed during routine inspections, especially during the early period of a ship's life, when the perception is that the ship is brand new out of the box, so nothing should be wrong with it. But once a crack is formed, it spends almost 80% of its lifetime in the region of a short crack before it finally starts to propagate fast, leading to failure. Repair of cracks involves cost and time, and given a ship's charter commitments, it may not be possible to repair cracks on a priority basis once they're identified. Under such circumstances, the focus has always been to determine and control crack growth conditions before final failure. NDE, or non-destructive examination, can be used for finding subsurface cracks, but can be expensive and time-consuming. Other elements of visual inspection can be surface cleanliness, lighting level, inspector stress, or viewing distance. Once a crack has been found, a repair procedure, depending on the severity and location of the crack, must be put in place. A newly built ship is expected to be crack-free, and cracks are unlikely to be caused by operational issues such as corrosion or fatigue. Design and construction or conversion related issues are most likely to be in the hull structure during this period. To reduce the possibility of missing cracks, the shipbuilder, class surveyors, ship owner, operator, through visual inspections and NDE can hopefully identify any flaws. But ships are complex and very large welded structures, and it's difficult to manufacture them without introducing some structural blind spots. There will be some sort of flaw, notch, discontinuity, or stress concentration. The normal procedure followed once cracks are detected during inspection is that they are gouged and rewelded, followed by non-destructive examination. Okay, so we're going on to the problem with side shell cracks as an example. So ship structures are subject to cyclical stresses due to wave pressure, ship motions, loading conditions during operation, and fatigue is important design criteria while designing and building ships. The science of cracks is really important as well. Forensic investigators and class surveyors. For instance, on the slide you can see in front of you, there's defect crack locations are in the aft portion of the hull of this vessel, which was the original section. So this is a vessel that's been lengthened. Backing brackets were not installed in way of the side shell during the conversion or new build. So on the left-hand side image, you can see where the transverse bulkhead meets the longitudinal side shell, cracks have formed. The cracks originally appeared at the bulb collar plate weld connection on the aft side of the bulkhead. Backing brackets were fitted during the repair. An existing temporary doubler repair was put in place. As you can see here, these are photographs of where the crack has formed through the longitudinal stiffener that's attached to the side shell. And the cracks were drill stopped in the side shell to stop propagation. So how do we go about repairing cracks in the side shell? With an SPS solution, as you can see in this image, the doublers were in place with a new longitudinal sectional stiffener. On the outside, to stop the ingress of water through the cracks, a Mico match was applied. Then we marked out on the longitudinal stiffener a line to be cut to try and remove the doubler to gain access through the temporary solution to assess if the cracks had grown since the temporary solution was put in place. So we removed the upper doubler plate and lower doubler plate. In the center images, you can see we removed the wooden bungs that were in place at the aft end of the crack arresters. We fitted new brass plugs and we trimmed them flush to the side shell plating. We then ground the cracks to create a smooth open profile. After which, looking face on to the side shell from the inside, you can see over 3 bays is what we call it, where the cracks are identified with orange, and the new stiffener has been, a section has been removed as donated by the green. So then we install SPS. We need to surface prepare the area back to 60 microns. So we prepare that and clean it. We apply moisture tolerant sealant and structural sealant over the cracks to stop any moisture coming through. We fit and tack backing bars, as you can see in red, around the perimeter of the area, including top and bottom of the web frame. Once that's in place, we then position plates on top of those backing bars, creating a seal cavity. Once the seal and the welds have been put into position, you have one formed cavity where the cracks are now inside, although behind the longitudinal stiffeners, they're inside that seal cavity. SPS polyurethane then is injected from the bottom of the cavity and fills the space between the new plates that are in position and the hull where the cracks have formed. Why was SPS chosen? And what was it chosen for? SPS was chosen to strengthen the area so the cracks wouldn't grow. With the fracture assessment and FEA, we calculated assuming that the diesel tank where the cracks were was full, and the fatigue assessment was performed with dynamic external pressure for the loaded condition of load cycles for 20 years. The calculated dynamic pressure corresponds to the large stress range during the service life, 20 years. By using SPS, the stress range decreased by 95% compared to how the side shell would be without any stiffening. The fatigue life is calculated to be 2,116 years after the SPS repair has been installed. So with the class society interface, they said the cracks were close to the transverse bulkhead, and the consequences with even a small crack growth was high. The cracks were covered by an SPS panel. Class wanted to ensure that the crack could not grow uncontrolled for a period during inspections. Class calculations showed that SPS panel between the existing stiffeners contributed to low stress level in the cracks, and the fatigue analysis showed low probability of further crack growth. The application for steel parts of the SPS solution, a review of the drawings checked if material selected was acceptable with respect to manufacturing method, weldability, and material testing. The drawing review also covered acceptable details according to the rules for fabrication and testing of offshore structures. The second case that I brought to attention is the Aframax double hull tanker crack. This crack was made the inner side skin knuckle in one of the cargo tanks on the Aframax tanker. In addition to a conventional pair, was added SPS on top over the knuckle for the entire length of the tank. The objective of the SPS was to reduce stress levels at the joint and also to provide an additional barrier between the oil tank and the adjacent ballast tank, adding an extra margin of safety against oil entering the ballast tank. So the solution to assess the service life fatigue performance of the knuckle joint, the structure analysis was carried out. The effectiveness of the SPS repair was investigated through finite element analysis, using two models to represent the as-built structure with SPS. The use of SPS as a permanent repair is effective because it reduces the stress levels at the knuckle joint, with a conservative assessment of 25% reduction in stresses at critical locations. So the fatigue life is improved by approximately 2.4 times. This, I put this in, this presentation is going to be available for some of these connection details for the Aframax double hull tanker crack and how SPS was attached to the side shell using the perimeter bars as a fully welded solution. Some photographs of the installation team, as you can see, the scale inside the tank, the SPS panel on going over the knuckle joint there. Since that time, regular inspections, there's been no reoccurrence of the cracking that we're aware of. This solution was also installed on 3 other sister vessels. The Ice Class 1A super vessel, we repaired cracked bulkhead plating. This project was brought to our attention by Lloyd's Register in 2013, following their discussions with the client regarding a life expectancy study of this already 22-year-old Ice Class vessel. The repair of the cracked bulkhead plating between the wing water ballast spaces and centerline fuel oil tanks. No single use can be attributed to any cracks that occurred on the ship. As I mentioned before, there's multiple or various amounts of issues that can cause the cracks. Cracking appears to be a result of a number of factors, compounded by the relatively long and continuous service in severe operating environments. Even new build vessels, when they're moving into ice regions, polar regions, due to the difference in temperature, can experience cracking. The purpose of the SPS installation was to inhibit future crack propagation, as well as eliminate the possibility of cross-contamination in the event of crack propagating through the full thickness of the bulkhead plating. And I've been shown the drawings there for reference. The cruise ship, we had a crack in the alleyway on deck 7. The photographs, as you can see here, this is a close-up view, and this is above the doorway itself. So the crack had propagated on both sides an SPS was installed to reduce the stress in that area and stop further crack propagation. So we didn't want the crack coming back after the repair was installed. A 40mm PU core of SPS was installed for this application. For ro-ro ramps, we've had several passenger ro-ro ferries with tilting ramps that experience cracking of the welds and plating at the point of attachment of the channel stiffener to the ramp plating, and it's all related to fatigue. They've been welded as initial temporary repair, but a longer, more permanent solution was needed because it kept on cracking. The transverse flecking of the deck tends to open up one-sided fillet welding joint, causing tensile stresses. There was substantial cracking. We did the finite element analysis and modeling, and it was due to the truck wheels where they were on the ramp. So we installed SPS with a 20mm core and gives long-term solution, permanent class-approved solution to the structural fatigue problem. FE analysis was used to assess the fatigue stress range. The tensile stress at the critical details was reduced from 155 megapascals to 22 megapascals by the addition of the SPS. The fatigue life of the structure, as manifested by this detail, is increased from just a few years to lasting the remaining life of the ship. For installation purposes, when we talk about SPS, I'll just show a little video here that I can talk you through about how SPS is installed. This is a sample ro-ro deck using SPS overlay. We're taking one small section at the moment. The existing deck is blasted back to original steel. Any holes are closed off using closing plates. In this case, we can reposition even lashing pots. Around the outside of the cavity, we weld perimeter bars to the existing deck, creating a boundary. In this instance, we've installed lashing pots to the center of the cavity and spacers to stop the plate from sagging into the cavity itself. The cavity size is approximately 10 meters by 2 meters. Top plate is welded to the perimeter bars, creating a cavity, creating a void inside. In each of the corners, the ventilation ports are fitted, and on top of the plate to stop it bowing up under injection and remaining flat, we put some beams that are held in place. A two-part chemical mixture is mixed at the lowest point of the cavity. Once it enters the cavity, it takes a few minutes to fill, and then after 10-15 minutes, it solidifies, bonding the new top plate to the old worn bottom plate. In some cases, the old worn bottom plate has corroded down to 50%,